Hello. This is the second part towards the alternating harmonic series video. Uh, you haven't watched the first video yet, and don't bother watching it because I feel that it was terribly explained. I don't know if you can hear, but in the first video there was a bit of nervousness in my voice while I was trying to explain things, and it also took like 40 minutes long to try and explain, although it shouldn't have taken that amount of time. Because honestly, compared to the other types of maths that exist, this is one of the easier one of the easier parts that we're exploring. But I still took an incredibly huge amount of time to try and explain that. Eh, But I'm hoping this will go better because this method where we're proving that the log of 2 is actually the answer towards the alternating harmonic series. So we're going to be exploring an easier way instead of a hard way like we did last time. And we're just going to jump right onto it. The method starts with the power series. If you don't know what the power series are, it's basically a sum. X equals to, no, not X. P is equal to 0 till infinity of x of p. So this is our series. This is the power series or the geometric series. It goes by both names, I think. And basically we can write this as 1 over x minus 1. Wait, no, 1 over 1 minus x. There's a big difference between those two. Yeah, so we can write this series as this single term here. So xp is just x0 plus x1 plus x squared plus x3 and so on. That would be equal to this thing right here. And it only works when x is less than 1, or the absolute value of x is less than 1. And it's easy to show why, because if you have something greater than 1, then this series is going to diverge, because uh, when you power a number that's greater than 1, like 2, you square it, you get an even bigger number. So you keep increasing the powers, you keep increasing the numbers, and they just keep growing. If you consider the case of a decimal where it's 0.5, where, for example, the answer to that is 0. Wait, what is the answer to that? Oh, 0.25. I had to think for a bit there. So it gets smaller when you square uh, a value that's less than 1. And because it gets smaller and the powers keep increasing, the numbers get smaller and smaller and smaller each time. So you're going to end up with a convergent value. Keeps going down and down and down. So yeah, it's convergent instead of divergent, and that's why it has a value right here. But of course, this thing is different than our alternating harmonic series. First of all, our alternating harmonic series is 1 plus 1 over 2 plus 1 over 3, or it's alternating 2. So just gonna turn this, oops, not like that. Just gonna turn that into a minus there. and so on and so on. You get the point. The thing is, this thing and this thing, they're two different things. Why are they different? I mean, that's easy to answer, of course, hopefully. Uh, but which parts of them are different? We're going to identify which parts of this thing is different than this thing. And once we've identified those different parts, we can modify this equation so that we can get an answer from here. We modify this. Wait, yeah, we modify this so that we can get an answer by doing the same modifications here because they're equivalent. So you add 5 here, that's the same thing. So we're going to do some changes here to convert this into this. So first thing, the the parts that are increasing, the p here, is at the exponent at the top here. So we have 0, 1, 2, 3, and the increase happens at the top. While for the harmonic series, we have an increase happening at the bottom. This is technically 1 over 1, so our increasing part is at the bottom. We have 1, 2, 3, those are the increasing parts, and they're at the bottom fraction, whereas over here we're at the top part. Second thing are the signs. We need to convert the sign from an always positive to an alternating towards alternating between negative and negative positives and like that. Uh, Other than that, we should be fine with everything else. Those two are the main changes that we need to uh, that we need to take care of. The easier one, the easy change that we have to make is the negative sign, where we have to convert the positive signs here into negative signs. Not all of them, only some of them. And that is actually easy to do. We consider our series here as negative x, right? So x can be any value. The thing that changes here is p. P goes from 0 all the way to infinity, while x is a constant. It can be any value you want. You can put 1 here, well, you can put 1 here, you can put 2 here, but those numbers don't work. So you can put 0.5, for example, x is 0.5, x is 0.1, doesn't matter. Any value works out. That's less than 1. Any value less than 1 works out. Oh, by the way, if you want to know why this formula is true, I'm sure if you look on the internet and on YouTube especially, there are many amazingly explained proofs as to why this is true. And so if you want to understand it, then I will refer you to those videos instead of explaining them myself. Oh yeah, so what were we about to do? We're about to turn this into an alternating series. So x can be anything. So if we set x as negative x, for example, we just convert the variables here. So if we set x as negative x, what we'll get here is an alternating harmonic series. Why? We can change x into any value that we want, any assumption that we can make, and we get negative xp equals to 1 over 1 plus x. And this change of variable is valid because, yeah, I hope through your intuition you can figure out why this is a logical step that you can take. Anyways, this will turn out to be an alternating series because negative x is just same as saying negative 1 multiplied by x and all to the power of p here. So we can separate it and that just becomes negative 1 to the power of p multiplied by x to the power of p. So this is an alternating series because we start where p equals to 0. So we start as negative 1 to the power of 0, that's positive 1, and then we move on, p equals to 1, and that's a negative 1. We go to p equals to 2, that's negative 1 times negative 1, so that's positive 1 again. Then 3 is negative 1, then p equals to 4, that's positive 1. So we have an alternating sign for the xp. So xp minus xp plus xp minus xp plus xp, and so on and so forth. So we have our alternating segment already. And now we want to find a way in order to bring the p downwards towards the fraction area. And there's actually a cool way to do it. I'll let you think about it for like 30 seconds or something. Think about the possible ways that you can transform something like x of p. What, yeah, like x of p. What can you transform this into? Oh, like what transformations can you put in place onto x of p? Any function that transforms x of p into something else. So it's particularly easy to do that with the help of calculus. Think about the two things you learn in calculus: differentiation and integration. What happens when you differentiate x of p? We get p xp minus 1. That's the differentiation. What happens when you integrate it? We get x p plus 1 over p plus 1. And those are valid transformations, just like how we transform x into negative x. We transform x of p into pxp minus 1 and x of p plus 1 divided by p plus 1. We're doing the same changes here. And so which one do you think we're going to use? The derivative part or the integral transformation? The answer is we're going to use the integral transformation. Why? Because that places a p variable, that places a p at the bottom, and we want that to happen because if you take a look at the harmonic series, we have 1 plus 1/2 plus 1/3. The increasing parts here is p. P goes from 0 to infinity, so we want p at the bottom to go from 0 till infinity. We want p at the bottom so it can go from 0 until infinity, and the integral gives us a transformation that does just that. We successfully put the p from being at the exponential part to being at the bottom fraction part. And suddenly our series here, our geometric series here is slowly looking like our alternating harmonic series. Let's get rid of all of these. So we're gonna transform both of these with the we're gonna apply the same changes to both of these. We integrate this part, that's same as we integrate this thing here. And the integral and the sum can actually switch places because the sum of something, like say 1 plus 2 plus 3, and if you integrate all of these, it's same as you putting the integral inside. because this thing is exactly the same as the integral of 1 plus the integral of 2 plus the integral of 3. And same with the derivative. So it's something that can go inside and it's fine, nothing changes. So that's what we're going to do. The integral of p equals to 0 to infinity is the integral of negative x to the p is equal to, what's the integral of 1 over 1 plus x? That's ln 1 plus x. And we can take the negative section out. As we've seen before, negative xp is same as negative 1p over negative 1p multiplied by xp. And negative 1p is negative 1p will not be affected by the integral because we're only integrating x. So if we do the integral of this, negative 1 can go out because that has nothing to do with the integral transformation thing. and that has nothing to do with the integral, so it can go out. What you'll get is negative 1 to the power of p, the integral of xp, which is same as, we'll just write it directly, x of p plus 1 over p plus 1 multiplied by these together. So we've done the integral already and we can erase that part. And so we have this thing over here is the same as ln of 1 plus x. And this thing here, and what's next after this? What do you think we should set x as now? What do you think we should convert it to? Well, we're going to convert it to 1 because in the alternating harmonic series, the top part over here, which corresponds to the x here, is always 1. We have 1 minus 1 over 2 plus 1 over 3. The top part is always going to be 1. So we want our x to be 1 in order to be the same like that. Anyways, if we set x as 1 here, 1 to the power of anything is just same as 1. So this part doesn't matter. And we have the following series. And this is actually the same as the alternating harmonic series. If you take the first term of this sequence, negative 1 to the power of 0, that's positive 1. And we have 1 to the 0 plus 1, that's just 1. The second term of this sequence is negative 1. The second term of this sequence, where p is equal to 1, we have negative 1 to the power of 1. That's a negative sign there. And what we have on the inside, 1 over p plus 1. So 1 over 1 plus 1, that's 1 over 2. The next term will be 1 over 3. The next term after that will be 1 over 4. And this thing is thus exactly the same as the alternating harmonic series. And remember what we set x as before. We set x as 1. So we want to apply the same changes that we make towards both sides of the function. Both sides of the equation. So what do we get when we convert x as 1? We get log of 1 plus 1, which is the same as the log of 2. And there we have it. It's proven that the log of 2 is the same as the alternating harmonic series. It's much faster than the way we previously did it, but it's also much more shallow, as you can tell. We discovered many cool things in the first part, but the second part is pretty boring and basic. But yeah, it's a more simple way to describe why an alternating sequence with uh, to prove why an alternating series with an increasing bottom part. I still haven't figured out which one of them is a denominator and which one is a numerator. But yeah, it's a great way to prove why the the alternating series with a bottom part that's increasing gives out ln 2. It's pretty cool how two seemingly unrelated things can become related with the power of maths. And yeah, that's it. Bye.